At first glance, this robot hand seems to be moving randomly, but it's grasping your attention with something else. It's shadow movement. For thousands of years, shadows have served as a powerful medium for visual abstraction and storytelling, from prehistoric cave art to shadow puppetry and hand shadow performances. Similarly, robots can actively adapt their morphology, allowing them to generate a diverse range of shadow representations and perform expressive shadows to communicate. However, teaching a robot to create shadow art is challenging. The same shadow can be produced by many completely different hand poses. Looking at a shadow alone doesn't tell the robot how its hand should move. The hardware presents another challenge. Human hands naturally block light between the fingers. In contrast, conventional robotic hands leave visible gaps, allowing light to leak through and breaking the illusion. To perform shadow imitation, the robot must capture the fine-grained details of the shape as well as the dynamic movement of the shadow that convey expressive information. To address these challenges, we developed a 21 degree of freedom robotic hand with a rigid skeletal structure covered by a compliant soft skin. The soft outer layer minimizes light leakage while preserving dexterous finger motion, enabling the creation of continuous and expressive shadow silhouettes. We model our hand in simulation using the skeletal structure as the collision geometry and a visual mesh that matches the soft skin as the light-blocking geometry. Our method begins with autonomous exploration, allowing the robot to learn a task-agnostic shadow self-model, a differentiable mapping between hand configurations and their projected shadows. Given a target shadow image, the robot optimizes its hand pose by back-propagating shadow reconstruction errors through the learned self-model. The solution is then refined with collision-aware optimization in a physics simulator. This enables the robot to accurately reproduce individual target shadows. To imitate an entire shadow video, the robot first extracts a sparse set of representative keyframes that capture the essential structure and motion of the sequence. During optimization, it places additional emphasis on visually expressive regions, such as an animal's eyes and other motion-critical areas, while enforcing temporal consistency across consecutive hand poses that respect the hand collisions. With this framework, the robot learns to perform sign language, varieties of hand shadow puppetry, and even imitate animals, such as birds and wolves. It achieves these without copying their physical bodies, but by reproducing the visual abstractions that people naturally recognize. Shadows are only one example. Humans constantly create representations of themselves through silhouettes, reflections, mirrors, avatars, and many other visual abstractions. Perhaps future robots will also learn to understand and control these representations, communicating not only through their physical bodies, but also through how they are perceived. Rather than asking, "What is my body doing?" the robot begins asking a different question. What will another observer see? This work is one step towards robots that reason not only about themselves, but also about the abstractions they can create.